So welcome to demonstration of video 5 on confidence intervals and prediction intervals. So we were dealing with some data before on heights and weights, and we'll continue to deal with that. What we want to do is predict a 95% confidence interval if new height was 1.5, and this is for the confidence interval for the um, mean if there was a bunch of different heights of the same value. So does it mean if the new individual with a height of 1.2, 1.5 comes along, it means that the average of a collection of people with the heights of 1.5, what their inferred weight would be. So that's a confidence interval. So if we run that here, we can see that we get a fit about 32, but our lower upper bound are very, very wide range. It's a very wide range here, indicating that there's a lot of uncertainty about this model. So what we can do is we can change the confidence interval if we want. We can change it to 75%, but then again, there's the quarter chance that our population mean for that value of 1.5 won't be contained in this interval. So you see that goes from 17.7 to 46.3. And what you'll note as well is that we have this model of the heights and weights that are being assessed. So we have a data frame with height equals 1.5. So if we change this data, so we see height there is listed as the column name. If we change it to height 2 or weight 2, which we had from the previous question, which should still exist. If we run this with height as the name here, we get an error. We get all these values input because it can't correspond this data frame to the one that we wanted. So what we need to do is change this to be height 2. So this data frame instead with a different column name, and this will correspond to give us one value. So an estimated for that exact value only. So you can see there are fitted values of 5.88, and the range now is much smaller because we had a bit larger sample size for these two variables. If we move on to prediction intervals, it's the same formula. So we could try it from the data above, height 2 and weight 2. With height 2 changed, and we see a prediction interval. See that goes from minus 5.8 to up to 17.5. So that's very wide, really. We could change that to 0.75 to get a narrow prediction interval, but again, we're going to miss something. So you can see there, prediction intervals includes any potential data point that might come along with the data we have so far. See, it's very, very wide distribution. So you can see that with height 2. There we see the summary there, and its variance. So its mean is 3.85. This variance is going to be about 10.9. Hence, we get a wide spread of values. Of course, we can't have negative heights, so this is just a kind of theoretical. We can imagine that there are normalized heights and weights, for example, partially normalized. We can change the sample size of this and repeat this. So this time we're looking at same mean heights and weights and standard deviations, but for a larger sample size. So we're calling these variables height 50 and weight 50. We can plot the data, look at histograms for each of them, and see that they're quasi normally distributed, and do the same for this. And what we'll see is that even though they have the same mean heights and mean weights, which we saw before of 2.5 and 46.6, if we do this, we'll find the confidence intervals are now much narrower. So it goes from about 43 to 60, right at a fitted value of 52. If we get the prediction interval, the 95% prediction interval for the same data, again, we get values that are more narrow. They're not very narrow, but they're narrower than what was the sample size for 50. If we change this to 5,000 and just repeat this, we see our confidence interval is now narrower again. It's 46.5, 45.5 to 46.9. Our prediction interval, as you'll guess, is also narrow, but not as narrow. And that's because that's affected by the underlying heterogeneity of the data itself. So you see there's a wide amount of variation in our data set here, to put it simply. So if you look at the standard deviation of the weight, you see that that's quite high. So if we square that to get the variance, that's going to be quite large. Sorry, that's weight 50 by, yeah, it's going to be quite large. So the prediction interval reflects the underlying heterogeneity of the data. So what you can try is using your own data, create 85% confidence interval, repeat this prediction intervals, and what you observe at the lower and upper bands when you do that. I can change the sample size to see how this affects the confidence intervals and the prediction intervals. You can also consider what coefficients you have for that model, and we can look at that summary we had before for our model, and we compare it to ones with a large effect here next, and then we can plot height 2 and weight 2, and you see they're highly correlated. The correlation is extremely high, it's about 0.99. If you look at the summary, you can see that the residuals are relatively small. The t-stats associated with the slope and intercept are very, very small, even though these estimates themselves are not huge. But you can see that there's a clear positive trend between them in this plot. Just adding a grid. And then if we look at the confidence intervals and prediction intervals, we just take that only, you see the confidence intervals are going to need, so we're dealing with height 2 and weight 2 here. Again, these have to agree. We have CI, we look at CI here. We can see those different values that are estimated. And if we look at that for the prediction intervals, we can also estimate those as well. That's for a range of values too. So we're not specifying any figure value for height 2 here. So you do that for PI, we can plot these against each other. I look at a correlation line between them all, weight 2 and height 2. If we plot height and weight 2, so we're going to remove these limit, x, y limits and plot these. We need to complete the PI prediction interval function. So we see the plots there. We can add an outline in light blue. So we see going through them. So indicating the intercept is about where is it going to be? 2 point something, 2.8. And the slope of the line is about 1. We can add on the prediction intervals by sorting, so the confidence intervals by sorting those values for the confidence interval, and then also the heights as well. So we see here that we have the wrong variable. So we see here that we have the confidence interval for the heights being plotted, and the same for the other on the other side in the green dashes, and then we have to change that for the prediction interval and plot those in red as well. So you can see that they're wider, reflecting the underlying data. And if we look at the correlation, then here we can see that's very high, about 0.99. We can also use this calculation function confint to get our confidence interval for weight 2 and height 2 as well, which is convenient too. So you can see there our confidence interval for the intercept goes from 2.4 to 3.12, and height 2 is from 0.95 to 1.05. And these are narrow estimates because the confidence interval for each the number of samples is very high, and therefore our estimate is more accurate as a consequence. So let's talk about more of this in class itself.